expected to get to G3, and then at G3 or higher levels, we pick up the phone, we dial a number, and every single entity in the North American power grid gets on that phone call. Because no president wants to be in charge here in the United States when we have a major collapse of the power grid. And when I say major collapse, I'm not talking about a few city blocks. I'm not talking about a few townships. I'm not talking about just a few counties. I'm talking about states, meaning significant chunks of the United States.
Certainly some food for thought.
This is why one of the former FEMA directors here, this is what kept him awake at night. John, I didn't talk about the December 14th event. You want me to bring that up real quick?
After my previous video on solar storms, I had more questions than answers regarding space weather and its potential impact on us and our society. Fortunately, not everyone is ignoring this. Today, I had the privilege of speaking with Shawn Dahl, the service coordinator for NOAA's Space Weather Prediction Center in Boulder, Colorado. In our conversation, Shawn details the types of 24/7 monitoring being performed on our sun, as well as the protocols put in place for when a super solar storm strikes. During his 9 years at the Space Weather Prediction Center, Shawn has witnessed many chilling events, some of which he details here today. And fortunately, through his and the Space Weather Center's efforts, many catastrophic events have been averted, but it still keeps people up at night. Shawn is an incredibly engaging speaker and was nationally recognized by the National Weather Service for his outstanding achievements in educational outreach. I was truly honored to speak with him, and I hope you enjoy learning as much as I did about space weather and what it means for us here today on planet Earth. Enjoy. I guess before we begin, would you mind telling the viewers at home a little bit more about your background and what are some of the things that led you into being a space weather forecaster?
Yeah, sure. I'll get into my background first, a real quick version. So I'm a North Dakota boy. I was born and raised. Started going to college in North Dakota in environmental science. And then my interest shifted as I was taking these classes more into the physical sciences, especially meteorology and geology and these kinds of things. So then I left after a couple of years and joined the Air Force for what I thought was going to be a 4-year stint, and ended up being 22 years later. So I had a full career in the Air Force and meteorology, doing regular weather forecasting, and that is where I became exposed to space weather. I spent 6 years of my career either observing the sun and reporting on activity or forecasting activity from the sun. So bottom line is I continued to take college classes and eventually got a minor degree in weather technology and applied meteorology and a host of physical sciences. So all that coming together brought me to be able to do what I am today. But after 22 years in the Air Force, when I retired from there, I went to work doing regular meteorology for the Air Force as a civilian for 5 years in Illinois, and then went to the Weather Service in Hawaii for a couple of years, and eventually here where I've been the last 9 years. And I'm quite happy. This is my ultimate goal, was to do this work. So now I'm the service coordinator here and still a space weather forecaster, obviously, as well. My interest in this stuff, in the sciences really, but in astronomy, as you see by my telescopes behind me, and in regular meteorology, came from my time in North Dakota. And in particular, a total solar eclipse went over my hometown when I was in middle school. And that just enthralled me and got me interested in the sun and astronomy. And now I have the best of both worlds as my interests.
That is so neat. Yeah, I can see that you're really passionate about space and space weather. That's terrific. Did you catch the 2017 eclipse?
I did. I took photos.
I'm sorry, the recent 2024 eclipse too, I guess.
No, I had plans to go to that one, but 3 things came up that prevented us from being able to go. So we had to scrub that trip and did things more local. But the 2017 eclipse, just up the road in Wyoming, an hour and a half, 2 hours away, allowed me to take a picture of the total solar eclipse there where my finger's pointing. The diamond ring effect was from there. So
wow, that's an incredible photograph. Yeah. Well, it sounds like you have quite the background. I read somewhere where you had recognition from the National Weather Service.
Yeah, that's true. That was a National Weather Service level award for education and outreach. So that's one of my jobs now as service coordinator that I was doing as a project as a forecaster. And they thought so highly of it that it got me a national recognition in the Weather Service, and I was the primary award winner in education outreach for the whole Weather Service. So that was a pretty cool and humbling award to receive.
That's really incredible. Again, I'm honored that you're here today. I guess in your own words, then, would you mind describing a little bit about the Space Weather Prediction Center, or SWPC, like some of its operational objectives, its missions?
Yeah, sure. The Space Weather Prediction Center, or as you said, SWPC for short, we generally just call it SWPC. So if I say SWPC, okay, that's what I mean for everybody and the viewers here. So sure. Yeah, our mission is safeguarding society with actionable space weather information. That pretty much sums it up on what our importance is, which is monitoring the sun for solar activity of importance that could ultimately reach or affect Earth or the near Earth environment, because space weather can impact our way of life, especially our critical infrastructure in the form of the technologies that we rely upon, whether they're in space and satellites, or whether they're our electric power grid, communications, you name it. Most of these things can be impacted by space weather, especially when we start to get to those severe extreme levels of activity. So our job here is not only the forecast operation, which is the heart of SWPC, the 24-hour, 7-day-a-week operation. I worked the overnight shift last night from 8:30 at night to 6:30 in the morning. So that just goes to show you that somebody's always got to be there 24 hours, 7 days a week. But surrounded outside the forecast office, we have a host of world-renowned scientists, information technology folks, administrative, to work our operation as a center going from research to operations, and operations needs back to research. So we really are expanding. We're even going to have a test bed. What that test bed will do is bring in like new models that are trying to predict space weather activity for potential use in operations, bring users in the community, whether it's aviation, the satellite operators, emergency management, whoever, in for occasional exercises to host and see what their needs are and are they being met and what can we do better. So there's a lot going on here at SWPC, and I'm proud to be part of that organization.
So what are some of the, you mentioned the solar activity. What are briefly like some of the phenomenon at SWPC? Is there like a long list of different activities? Does it include things even outside our solar system?
Sure. Yeah, for us here at SWPC, we're focused more on the the sun to Earth line. So anything in that realm that could impact or affect Earth is what we're responsible for forecasting. There are space probes and, the Mars rover out there. So NASA looks at space weather activity basically for the solar system, because there's these missions that they're responsible to know whether something is going to impact that particular spacecraft out there. So what we're looking for, all of us, NASA and here, but I'll focus on SWPC, is the types of storms that come from the sun. Whether it be a solar flare, this burst of electromagnetic energy across the spectrum in the form of X-ray flux or radio burst emissions on different frequencies, solar energetic particles in the form of electrons, but in particular protons for the main energy level ones that we're concerned with. And those can cause the solar radiation storms. And then the coronal mass ejections, these large bursts of solar material that fling off the sun, carrying an embedded magnetic field with them. That's essentially what a coronal mass ejection, or CME, is. And the last feature I'll bring up, there's others, but is the coronal hole. And a coronal hole is a large feature on the sun. They can be small, but oftentimes they can get quite large as we come down from peaks in activity through a solar cycle. And that's where high-speed winds can escape faster from the sun and the solar wind and also cause these geomagnetic storms. So both the CMEs and the coronal holes can cause geomagnetic storms. And what that is, really quick, is just a magnetic storm around the Earth. But that relates because electricity and magnetism are kind of tied together. And that can influence the electric power grid as one instance.
Interesting. So the coronal holes as well as the coronal mass ejections can induce power fluctuations in the grid.
That's correct. They can bring up what's called geomagnetically induced currents, or GIC for short, essentially spitting up amperage onto the high voltage transmission lines that are not wanted, because they can Oftentimes, well, they're direct current, and we work on alternating current systems, so that's one problem. The other problem is that they can overheat the transformers because of that extra induced current showing up on the grid. We here at SWPC, we have a model that helps us determine some of that, and that shows us volts per kilometer. And normally that's measured in millivolts per kilometer during routine activity. When we get to 1 volt per kilometer, that's notable. They will notice stuff on the grid in certain parts of the country. We get to 10 to 12, that's going to be impactful, meaning they're going to be dealing and taking mitigation measures in some of these entities of the power grid. And things that go higher than that could be very problematic.
Wow. What are some of the highest signals that you have seen?
Myself, here in the 9 years I've been here, this model hasn't existed the whole time. It's only been around the last, I think, wow, I'm losing track already, somewhere around 3 to 4 years. The highest I've seen is single digits, but volts per kilometer. And the grid was noticing that. One of the most recent storms we had, which was back at the end of March, we got to quickly to a G4. We have a scale of 1 through 5 that I'm sure we'll talk about here later. 4 is near the top end, not the top, but that's severe. G5 is the top of the scale, and that's would be called extreme. We got to a low end G4, and they noticed it, especially in Canada. Some of the mitigation measures were taking place, and one of the pieces of equipment they used to help deflect or reroute this extra current to ground it tripped. So it was doing its work, but they were also doing their mitigation procedures to make sure there were no interruptions or problems with the power flow. So they were taking actionable measures to make sure there were no issues with the grid.
Right. Wow. Which part of Canada was that? I was just out of curiosity.
It sounds like it was somewhere around the Ottawa area, but in particular up in the British Columbia northern areas, it was noted. And, people may think, well, it makes sense to have the northern part. Well, that's true and not true. Oftentimes, it doesn't work that way. And when we get these builds up in activity, usually this is a nighttime thing that we'll notice as the storm picks up and progresses. That's just because where most of the energy intrudes into our magnetosphere, our magnetic barrier, is through the night side. But this was a dayside event. It came in during the daytime, and that to have the levels that we reached in the daytime was really pretty remarkable and I'm not going to say extraordinary, but very remarkable. And if that had continued to progress throughout the whole afternoon into the night or overnight hours, the United States would have seen a pretty nice aurora here in the upper Midwest, northern parts of the country, maybe down even further into the lower Midwest, because it was ripe. We had a pretty strong CME, and I'll talk about it later, perhaps with one of your questions of why that didn't happen, because the potential was there the whole 24 hours plus that the CME was passing over Earth. Wow.
That's incredible and maybe a little chilling as well. So we have lots of data that's constantly coming in through this SWPC. Would you mind maybe highlighting some of this data that's on the main website? I could share my screen too.
We have a lot of information on the site.
There's a lot of information.
Yeah. So we try to make as much as possible freely available. Why? Because we're taxpayer funded. I mean, this is a government operation, so we have to be as open as possible with the information and let everybody use it, whether it's national here in the U.S. or international. Other countries can go all over our webpage just like any citizen of the United States can, because that's just the way it is. It's science, and we want it freely available. So we have various observational data on there, whether it's what kind of sunspots are present on the sun, what does it mean, what are we forecasting. Some of this is coming from observatories on the ground, such as one I worked at in the Air Force for 4 years, monitoring the sun through a telescope and doing sunspot drawings and reporting that not only to the Air Force, but here to the Space Weather Prediction Center, and reporting on solar flares that are optically seen with the telescope. Radio emissions coming from the sun that can be highly important. And if we have time or it comes up, I'll talk about the big event on December 14th that was unprecedented because of a radio burst of energy from the sun that was impactful to aviation here across the whole country. So an interesting story there.
Yeah, I'd like to come back to that.
Yeah, sure. We have forecast information models, some of which we're on the screen right now. The ovation model in the top right corner kind of gives a basic idea of where the aurora might be seen based off current solar wind conditions that are going on, kind of a 20 to 30 minute forecast roughly of where the aurora might be visible. We do not do, just so everybody's clear, we do not do aurora forecasts here at SWPC. We leave that for the private industry, but we do have models because this model is important. It gives us an idea of where the auroral jet is, and that can impact communications as well, but it's not really a true aurora forecast. You see on the middle screen in the blue is one of the satellites in space that monitors the sun's outer corona for us. This is how we look for coronal mass ejections that are departing the sun. Right now, as it's playing, there are some weak, faint ones that are moving outward from the sun. And then the one to the left is our GOES satellite, our NOAA-operated satellite that not only takes pictures of clouds near Earth here for regular meteorology, because it's a meteorological instrument, but it has a space weather observatory package on there too. So that's how we get a lot of our near-Earth measurements of X-ray flux for flares, protons for the radiation storms, and electrons that can be problematic for spacecraft as well. And also the imagery that you see there. And the last two that have gone up have had an imager on there.
These are pretty incredible images. So are these dark spots on the sun, are these coronal holes or are these
Those
sunspots?
Are coronal holes. That's exactly right. So we're looking at the very lower corona here at this particular wavelength of light and temperature. So very high temperatures here. But it's those dark areas, not all of them, but the one in the kind of middle to the right there, yep, you got it. That's a true coronal hole right there. It's a smaller one. But that's where magnetic fields, most of these are localized when they punch through the surface of the sun, and ultimately they can lead to sunspots. But some of them have the magnetic fields going all the way out into space before they come back and connect back to the sun, and that allows the solar wind to escape faster. So that's where we can see increased speeds when those speeds that leave the sun at center disk, as the sun's rotating, it looks like it's moving from left to right. But at some point in time, they eventually reach Earth, and that's when we can see wind speeds go up just from a coronal hole activity.
Wow. And then some of these data panels below. So are these connected to the above images, or are these sort of separate images?
Not really. No, the ones in the bottom right now, the GOES X-ray flux on the left, that is telling us the X-ray energy coming from the sun. So those little upward spikes, those are flares that have been going on. When I was on the overnight shift last night, we had a couple of M flares happen. The categories are marked on the right. You see that A through X as you go up the scale. The normal background X-ray flux from the sun during solar minimum, when we have very little activity and months without sunspots, kind of marks the beginning of a new solar cycle as we come out of solar minimum. Then that's usually at the A and B levels. As you start working your way up to solar max, the background can be at C-class levels like we are right now. And then the true NOAA space weather scales for solar flares. So you have your activity and your flares going on, but they don't become strong enough to cause HF communication degradation until we get to the M level. M is where the 1 on the scale begins, so the R1. And M5 would be an R2, X1 is an R3, and then from there it's every 10. So X10 is an R4, and X20 and higher, we can't measure beyond that, would be a true R5 level event. And then, the one next to the right on the proton flux, that's the energetic protons coming from the sun that lead to radiation storm potential. Right now, it's pretty flat line in the bottom. That's because that's our background level. There's no energetic protons in abundance swarming over Earth right now. But that instrument is critical and key for us to detect those particles because they quickly lead to the S levels on our scale. The one to the right of that is the geomagnetic response. That is not on a satellite. The other two were on the GOES satellite. This one here is a 3-hour estimation of what the geomagnetic response was. And to do that, we use something called the KP index, which you see on the left, which is 0 through 9. Each of those is divided into 3s. So we have kind of a low end, which we call minus, a middle end we call Z, and a top end we call P for plus. So every one of those numbers would have those 3 levels in there, except for the 9. The 9 has a 9M, and then it's just 9, because we can't really measure anything higher than that. Why is that important? I should tell people we send our first warning out at KP of 4. When we get to a KP of 5, now we're at G1 on our NOAA space weather scale. So it gives you an idea that you have levels that are important, but when they get to a certain strength, now we start talking about NOAA space weather scale activity. And every next number is the next number on the scale. So a KP of 5 would be G1, a 6 G2, and so on until you get to KP of 8. And this is why it's important for people to know. A G4 is KP of 8M all the way up through KP of 9M. The top end of the scale, KP9Z, if you will, which we can't measure more than that, is a true G5. So G4, you have 4 levels, really. So you can see right there how extraordinarily strong we have to be to get to a true G5.
You said so K4 is when alerts start going out.
Yes, that's when we do our first warning and alert when we reach that level for the first time. The KP of 3 we call unsettled. So it's a little active, and the aurora can spin up over Iceland and Alaska and places like that, northern Canada. KP of 2 and below we just consider quiet conditions, so not much happening, lower levels like that. Believe it or not, KP of 3s and 4s are actually of interest to certain communities, whether they're precision engineers working on electronic computer chips and stuff. They have to be very careful, and conditions have to be perfect. So they use our information for that. And then there's other businesses out there, including some really strange stuff, but they need to know about just KPs of 3 and 4. And we don't alert on any, the KP of 3s or lower, but they're using our webpage for this information in our forecast.
I'd imagine some very sensitive electronics and things. These would be highly impactful on those sort of instruments. So on this middle panel here with these coronal mass ejections, how fast is it determined from when the ejection occurs and then if it's earthbound or when it strikes us?
Sure. So I'll go into a little detail about CMEs and then kind of give everybody the timeline of how these work. So a coronal mass ejection, as I mentioned earlier, is basically a piece of the sun ejecting off into space. Now, the sun is so massive, there's so much to it, when it sounds extreme, like, the sun could suddenly lose itself through these CME blasts. No, it's constantly revitalizing itself over and over. I mean, it's not going to run out of problems here for millions and millions of years. But these are billions of tons of solar material that fling out into space. And buried in there is these strong magnetic fields. Why is that important? Because not only is it the push of the solar material when it hits Earth's magnetosphere, but also that embedded magnetic field coming with it eventually is what really wraps and can connect with Earth eventually. So when there's activity we can see on the sun, whether it's a solar flare or some of the imagery that we were looking, like the one that saw the coronal holes, there's other temperatures we can look at as well that give an idea of activity. And we as forecasters, things that we can see in the imagery when we have a flare, or not even a flare, maybe something called a filament or prominence is blasting off the sun, that can give us an idea, we may have a coronal mass ejection on our hands here. So there's the Air Force reporting radio events and activity. There's a couple of signatures that tell us that there's material moving through space just because of the radio signature that they're picking up, which is really cool. So we may see that come in and say, okay, we probably do have a CME on our hands. And then we won't really know, though, until we get the coronagraph imagery in that blue image you were showing in the middle top. That's where we see the coronal mass ejections leaving the sun, and that's what we begin to measure and analyze as forecasters. And that imagery is fairly timely most of the time, meaning we can see an updated image every, 30 minutes to an hour and a half, which isn't really good, but it's not bad considering what we have out there 1 million miles from Earth. It's the only instrument that does this for us right now. And it's old. It's decades old. But let's say it is on time and it's reporting, it's being tracked. Then we will see that imagery come in. Once we get enough images, then we can, watch its motion and watch how it's expanding. And we can start to analyze and try to parameterize that particular CME and its motion. And then we'll submit that analysis into our what's called the WSA NLO model. And that's available on our webpage as well. And that will tell us when it may reach Earth, and will it pass above or below Earth, or will it hit us completely? And, very slight deviations in the analysis of the CME that each forecaster does can make extraordinary amounts of difference. I mean, 93 million miles away is the sun. So any little changes make an extraordinary difference in time or, Earth-directed component or not. But once, let's say everything's timely, we get some updates, maybe after a CME has happened, we might have enough images to do our first analysis, probably at the best in about 6 hours. At the worst, it could be over 12 to 18 hours. Why that's important is because the fastest these can get here, we think, is 15 hours. So yes, we could have a period of time where we don't even get to look at one because This is a NASA research satellite, this coronagraph called SOHO-LASCO. And that means we don't have control here at NOAA. NASA may need to track something else, so they move their antennas to track a space probe out there and make communication with it. It's not an operational satellite. Fortunately, we are going to have a compact coronagraph go up on the next GOES spacecraft, which launches, I think, now in June. So we're hoping to have a near-Earth coronagraph in space. And then we will have control. That'll be a NOAA operational satellite. So we will get to say, no, you can't turn away from tracking on it right now. We need to keep it pointed. But anyways, wow. So the fastest we think they can get here is 15. Historically, it's been 18, and that's the infamous Carrington Event, which I'm sure we'll want to talk about here as well eventually. And usually they're about 2 to 4 days, however. So that's kind of the timeline of activity on observations and then how quickly they can get here.
That's interesting. Okay, so 15 hours is more of the upper limit on the speed when they arrive, but sometimes
correct.
Usually more like 2 to 4 days.
Exactly.
You had hinted on December 14th, there was some major events. If you want to talk for a few minutes on some of these significant events that have been detected with SWPC or during your time or in its history.
Yeah, I got a couple examples for you. Let's just focus on this solar cycle first. So we are in solar cycle number 25. We are nearing the peak of this solar cycle, which is now predicted to be later this year or early next year. But what's important for people to know about solar maximum, which is when we have the peak of activity, the sun can be full of sunspots. We can have CMEs flinging off the sun pretty routinely, like it's been happening in the last 3 or 4 days, is that it's fairly quickly over a couple of years to get up near peak, but then it's slow to come down. So what I'm saying is, if the peak is later this year or early next year, it doesn't mean, okay, now things suddenly shut off. No, this year, all of 2025, and much of 2026 are likely to be very active years where we could be the most susceptible to the severe or extreme levels of activity if they would occur. And then things will slowly begin to temper off from there. So already in this solar cycle, we've had some pretty extraordinary activity. We've had several occurrences of G4, so that's severe end of our scale, not the 5. We haven't come close to that yet. But the 4 levels we have hit several times already for various points in the year. And already this year as well, at least the one time quickly. We've had plenty of solar flares. We've had good numbers of R3 level events. We have not reached R4 as of yet. And right now, if people were to look at the sunspots on the sun, last night when I was doing my work, there was 14 sunspot groups on the sun. That's groups. Gosh. In those groups, there can be a large number of sunspots. So the sunspot number right now is pretty high. It might be near the highest of this cycle so far. But those regions right now are all not very magnetically complex. So yes, they've been pushing out some low-end M1, R1 level flares, but nothing as of yet that's reached up higher. And we're not quite sure that that is really likely to happen. We're calling it a chance at those higher levels right now. And we've had energetic radiation storms already, proton events bombarding around Earth and mitigation measures for those that are satellite controllers that need that information. But historically, so we're just kind of getting into the solar max right now. We've already had a lot more activity than was originally anticipated when the International Panel of Experts got together 5 years ago and tried to predict this solar cycle. Their prediction is much lower than where we're at right now.
It seemed like the prediction had been modified as of maybe December, or some original projections seemed to be a little bit skewed.
That's correct. One of our scientists here, one of our heliophysicists, he developed a good revision to the forecast. So it's not through the International Panel of Experts, but he is an expert. And clearly, and he created that whole modified forecast, which shows it notably higher. I'm not going to say significantly higher, but notably higher than the forecast. You can clearly see that we're more active than the original prediction was. But what's that mean for the cycle? I don't know. It means we could stabilize now and come down early. Does it mean we can continue to go up? Does it mean that we'll kind of reach the peak now and we'll just stay that way for a while and then come down? We don't know. The sun's still mysterious in so many ways. But yes, you are correct. That revision forecast will soon be available on our public webpage. Right now, it's privately held because it's still experimental. But once it's approved, people can see that revised forecast for themselves right on our webpage. We won't waste time putting it out there.
Yeah, I'll be on the lookout for that for sure.
And then some of the historical things prior to when I got here. 2003 was the last super significant activity where we were reaching G5 levels, and that was called the infamous Halloween storms of 2003 because it was around Halloween. And that's how our space weather storms tend to get named. We don't have to have a naming convention, and whether it's the St. Patty's Day storms of 2015 or the Bastille Day storms of whatever. This is just how it kind of works out. But that's when there were power grid collapses and problems in some other countries, not here in ours. They were dealing with it, though. Guaranteed they were dealing with it. But other countries did have collapses with some of their systems and equipment. And there were numerous issues with that particular storm. There was ones in the big radiation storm of 1972. So right in between the two final Apollo lunar landing missions. So 3 months earlier, astronauts had been on the moon. 6 months later, they were on the moon. Right in the middle, when nobody was in space, fortunately, we had one of the strongest radiation storms that we've had since we started recording this activity. And most of the professionals, scientists, and doctors think that that may have been caused really acute radiation sickness to the astronauts. There was some debate whether it could have been lethal or not. Right now, they don't think so, but they thought so maybe before. So it tells you there's still uncertainties here. And we're going back to the moon, right? So next year, we're going to have 4 human beings traveling around the moon. And then a year later, first woman walking on the surface of the moon among the others. And we will be part of that because we talk to NASA every day, whether anything's happening or not. We have a scheduled phone call and we communicate about space weather. And when we go back to the moon, we will have a forecaster in place for the duration of that mission in Houston at Mission Control to help converse and be the solar expert on space weather directly interfaced right there with NASA. And then later, I've talked a lot already, the 1859 storm, the Carrington Event. We'll want to talk about that at some point here to make the general public aware of what would happen if we ever had that kind of level of activity again in our technological age.
Well, we can talk about it right now. This is something that I'm very curious about. And I know it was 1859, so
yeah, that storm,
while ago.
Let's put it this way, its importance is so significant that this is really the underlying reason our federal government and international countries are invested in space weather and continuing to grow that enterprise because of its importance, because we're constantly relying on technology. It seems like more and more and more, right? What would we do? Most people wouldn't know how to read a map. That maybe sounds demeaning, but a lot of people just haven't picked up a map and normally read it anymore. They use their phone.
It's an experience. It's an experience. And not only maps, but also just making phone calls. Most people don't have landlines or any sort of...
Most people are just using their cell phones now. So yeah, we're relying more and more upon technology. You know, hey Siri, whatever. You know, you don't go to the library and have to look things up. It's all freely available. So we rely on that, and that's impactful. But the thing that we all rely on in the developed countries is electricity. So the federal government has a huge interest in space weather because regardless of political affiliations, so it seems, since we've been through 2 administrations now, and this interest continues to grow because no president wants to be in charge here in the United States when we have a major collapse of the power grid. And when I say major collapse, I'm not talking about a few city blocks. I'm not talking about a few townships. I'm not talking about just a few counties. I'm talking about states, meaning significant chunks of the United States. And since we're an interconnected power grid, this is going to impact other sections of the country that maybe aren't directly prone to these GICs, these geomagnetically induced currents, which can collapse the grid in the worst case. I bring that all up because in the year 1859, before we had the technology, the only technology we really had that was involving communications, and that was telegraph. People were smacking the metal plates together and sending a signal across the copper wire from one territory or state to another. I think it was September of 1859. There was an astronomer, Richard Carrington, in England, and he was doing a sunspot drawing. And while he was doing the sunspot drawing, he noticed 2 bright white lights show up around the sunspot group. That's very rare. He didn't know at the time, but what he saw was something called
on the paper itself. It actually illuminated.
Yeah, it's a very rare event. It's called a white light flare. I've never seen one in the whole time I've been optically observing, but he clearly saw it, and he put it on his drawing. 2 little kidney white light shapes around the sunspot group. So what that means for people listening is that the background level of the sun that's so blinding, that flare was so strong optically that it was brighter than the background light of the sun that we see with our own eyes, if we could safely look at the sun. Very extraordinary.
Oh my gosh.
And then 18 hours later, the sky lit up with aurora. People in Europe that had never seen the aurora thought there were chaos was going on. Maybe the world was going to end. People in the Caribbean islands were panicking. People in Colorado, it was so bright that they thought that there were fires going on just across the other side of the horizon or something. It was that magnificent. I can only imagine what that looked like. And to the telegraph operators, they were having problems. Sparks were flying from the batteries. They didn't have electric power. They used batteries, DC power. And something started on fire. All sorts of crazy things were going on. There's a conversation between two, they're called ditty boppers, the old language of telegraph operators, were communicating, and they were talking about their problem, and they decided to disconnect the battery. There was still a signal. They could still carry on a conversation. Why? Because the lines were so saturated with electric current that it was still generating and allowing a signal to be carried.
Oh my
what that
gosh.
means today, remember how I mentioned 1 volt kilometer is notable on voltage on the lines, on these high voltage transmission lines, and 10 to 12 is problematic. They're going to be dealing with the issue. This storm is expected that it could have been generating 100 to hundreds of volts per kilometer. That would be devastating. That would be catastrophic to our power grid, or so we think.
How much could it handle?
No, it's unknown. This is still a big controversial thing. The power companies will say one thing. The scientists who study this stuff may say another thing. So there's some that are on the far extreme that say we would be devastated. The electric power grid in the system would be gone for months if we had that kind of a storm happen again. Others say, well, hold on, maybe not so much. We're fairly resilient. Maybe this would just be some days. But either way, nobody likes to be without power for even just a few minutes even, right? Can you imagine days without power, weeks without power? Why? Because the transformers would overheat and burn up. And these are giant things that would occupy the whole room I'm sitting in here. And they're not plug and play. They have to be made and they have to be shipped. Most of them aren't even made in this country. They're from overseas. So yes, if we had a catastrophic collapse where we lost a lot of power, the last time a storm did that, by the way, was 1989, when 2/3 of the province of Quebec, Canada, lost power due to a space weather storm. All those millions of people were without power for most of the day. In the middle of winter, freezing temperatures. It was March.
Oh my gosh.
Not middle of winter, but it was March, freezing temperatures. The northeast part of our country came a sliver from having some collapse as well. Some equipment was damaged. It had to be replaced, but we still had the power grid maintained itself. That storm is thought to be over 10 times less the strength of the Carrington level event.
Wow. That's certainly some food for thought.
This is why one of the former FEMA directors here, this is what kept him awake at night. So he said, is that kind of Carrington level event today, and what would that mean to our society?
It's sort of a scary thought. Since the 1989 storm, would you speculate or know if Canada or northern provinces are better equipped for handling these than
absolutely.
United States?
Come some ways. There's things that they do. There's these things called GIC inhibitors. Maybe they have a different name in their world, but that's what I call them. And they're made to design like the one I talked about earlier that did its job up in Canada with this low-level NG4. So there's equipment out there that's installed to help divert some of this current or minimize it by sending it in different directions. However these things work. I'm not an engineer. I don't know how they work. But that's what they're designed to do, is help prevent the accumulation of amps of current on these high-voltage transmission lines. I talk about volts per kilometer. Well, they talk about amps. I mean, they notice it when it's, when you get into the high-end single digits, especially the double digits, low end, they notice it. They're taking and spinning up procedures to make sure that they're doing the things they're supposed to do to monitor that at the very least, or send manpower out, time and money, to go monitor a transformer, make sure it's not overheating. Let's bring up this line now running from wherever to wherever, because we have to monitor it more closely now to make sure there's not strangeness going on in the power flow. These are the types of things they do. So our job becomes busy with the activity going on, and we make our alerts and notifications to them. And by the way, people should know we do our best with all the customers we talk to: aviation, power, NASA, FEMA, National Security Council at the White House Situation Room. If we get to a G5, we will be talking to them. But we call the power grid. There's a hotline call we make. When we get to G3, expected to get to G3, and then at G3 or higher levels, We pick up the phone, we dial a number, and every single entity in the North American power grid gets on that phone call.
Wow.
They're called reliability coordinators. There's about 18 to 19 of them that string that whole section of the U.S. up into most of Canada. And they get on that call, and they listen, and they take note, and they start to spin up their measures. And even in the last one we had in March that we briefly reached G4, we did receive word from them that they were noticing it while we were on that phone call talking to them. And that's how I was able to give you some of that information here today. And that was just at a low-end G4.
It's interesting what's going on behind the scenes with infrastructure and all of the different factors that can influence it day to day. It's easy to imagine most people to not think about it, or just to kind of think, oh, well, everything's going to be fine. And I suppose if there's no problems, it ends up being fine, but it takes a lot of coordination. And I was curious because there's not a single power company that owns every grid, right? But you have hotlines to every entity.
Yeah, they're all cooperative, right? So they're all working together. We're interconnected, meaning that we can spin things in different directions and we help each other out. So there's, I don't know, it might be 4 now, but at least there's 3 main interconnections. There's the Western, the Eastern, and then Texas. What's called ERCOT. Remember, they had major problems with that one winter storm just a couple of years ago. So
that's right.
Yeah. So even though most things aren't going to directly impact that ERCOT area, they may be impacting the northern part of the Western interconnection or the upper Midwest and northeast part of the Eastern interconnection. Because we're interconnected, there's going to be shared or however it all works. People will notice it. That event I talked about where it's estimated that it could have had over 100 volts, somewhere between 100 and 1,000 volts per kilometer. That's extraordinary. People are going to see that anywhere in the country and in the worst, most susceptible places. And if people are wondering what I mean by that, just think about what you're standing on, what we walk on planet Earth. If there's highly resistive rock that you're built on, well, electricity needs to find a shortcut if it has one available. So if the material, the geology is highly resistive material, it's going to want to find that much faster and quicker. What is that? Transmission lines, electric lines, power lines, railroad tracks, pipelines, whatever where current can flow on, that's what it's going to do. Where's that resistive rock? Well, the Appalachians, the eastern part of the country up to the northeast. The upper Midwest, just because of their location, they're quite prone, and some of their geology allows that. Proximity to salt water is another inducer of current that it can cause current to flow a lot quicker and easier. So yeah, there's just so many things that go into that prediction. But I guess my line here is that, some areas of the country are more prone to others, but in a major storm, a catastrophic level storm, Carrington level event, all the power grid entities are going to feel that.
Do you have any recommendations or advice for the average citizen at home? I mean, awareness is one thing, but maybe also some simple precautions, protocols, or even things like alternative communication networks. I mean, is this anything that this sounds too apocalyptic or doomsday, or there's some practical protocols or advice that you could give in regards to that?
Sure. Yeah, a lot of what I said today, we're talking the extreme end stuff here, right? And we're talking very rare, very unlikely, right? But we are overdue. We are honestly overdue for an event like that based off what we know historically. So it'll come. It's just a matter of when. So I don't want to get people freaking out, panicking. But what everybody should always have anyway, because of terrestrial weather threats, is, backup generators. You should have stocks of batteries and check them out frequently and routinely. Have your weather radio. Have your emergency alert type systems that notify you in whatever capacity they do. That's the same types of things people should be doing when it comes to space weather. And most things they hear about, even if we get to G4s or an S4 event and such, the general public really doesn't need to take any action other than be prepared already with the things I've talked about. But when we start to get into those 4 levels of activity, they probably should begin to at least pay attention and monitor our webpage, swpc.noaa.gov, because we're the nation's official source for this information, to see what's going on and keep situational awareness. Because what will happen, I'm still trying to understand this completely, so I may be incorrect here, but I believe what happens is if we reach an S5, meaning a radiation storm at the top end, extreme, or a G5, top end extreme, FEMA's going to use their alert system and send that information out to all emergency levels across the country. Who's going to pick up on that? Who's part of that? Well, the press, the media, TV broadcasters, they will know about it because they're probably plugged into the same stuff. So people are really going to start to hear about it. So whenever we start talking about those levels of activity, absolutely, the general public should be paying attention and know what's going on. Not that there's necessarily going to be a collapse. Remember, we've had G5s before that have not influenced here, like the 2003. We had our issues, but we didn't collapse. Other countries did, but we didn't, because of measures going on, perhaps, or it just wasn't, it wasn't even near Carrington level. It wasn't even close. It was well over 10 times less that strength. The public just needs to pay attention, learn, use some of our resources on education on our webpage to be smarter about space weather. So when you hear a term and you hear something like internet apocalypse, whatever, you can kind of know already by looking for yourself that, no, that's probably unlikely. That's probably erroneous information because here's what I understand it to be. All that's out there. We have plenty of educational material to keep the nation's space weather ready.
Right. No, it's a tremendous resource. It's really helped educate me a lot more on the solar events on Earth.
John, I didn't talk about the December 14th event. You want me to bring that up real quick?
Oh, yes, please.
So we had something. The sun is always doing something new for us. I swear, it seems like it anyway. We always know about these things. We call them radio bursts. We've known about them for a long time. We just can't really predict them. We can predict flares, but we just can't predict radio bursts. What a radio burst is imagine like tuning into your FM radio station and just cranking up the volume max. It's just overwhelming, right? You have to plug your ears and close up. Well, sometimes the sun becomes that way on radio frequencies. So radio frequencies that air traffic control uses domestically across the country is in the range called VHF and UHF. They're slightly higher frequencies than one that solar flares impact directly because of what it does to our atmosphere. But on that particular day, we had a solar flare going on. It reached that R3 on our scale. So we should have just been experiencing high frequency communication problems, which 3 to 30 megahertz range. Who uses that? Well, aviation over the oceanic areas to talk to air traffic control because they're not line of sight. But domestically, it's line of sight. So you go to VHF and UHF frequencies. What happened that day is we had one of these radio bursts happen that was so massive that it seemed like the pilots, the communication between air traffic control and the pilots, like they were being jammed. They could not talk at all in some cases.
Oh my gosh.
It was so bad that if that event, it lasted about 8 minutes. That's a long time, honestly. If it had been much longer than that, I know Seattle, it seems, was probably going to shut down airspace because of the safety risk, because it was that bad. They just couldn't find frequencies to talk on. Why? Because the sun was jamming them 10,000 times the normal background level that they were used to operating on. Made it seem like they were jammed. They described it as being mic'd up, like pilots were just pushing down the mic but not talking, so blocking out the frequency. That's how bad that event was. It stretched pretty much across the country because it was the right time of day. It was the middle of December. What happens in the middle of December, in and around December 22nd? Winter. The sun is lowest in the sky.
The solstice.
So yeah, you have to have the sun in the background somewhere for that to happen. If it's straight overhead and you're talking to a plane over here, you're not going to have a problem. But if the sun's over there and you're talking to planes flying along the horizon, you're going to have a problem. And that's what happened that day, is everything kind of worked itself up. So that was a problem that was pretty much experienced exclusive to our country. Not so much to South America because the sun was more overhead at the time. And we're talking line of sight, looking at planes along the horizon and talking, more of an angle, not straight up. Yeah, it was an extraordinary problem that developed there and was very impactful. So now guess what? So now the FAA, the Federal Aviation Administration, and others are thinking, maybe we need to know more about these radio bursts. We've always talked about them, but there's only been a few times in history where it's been massively impactful, to include during the Cold War era when something similar happened and we thought the Russians were jamming us. And it was thanks to an Air Force weather officer at the time who was knowledgeable enough, he helped to avoid a worst case scenario, which could have been a build up to, another war. So
Yeah. It's always good to know about the exact source of the jamming event before making any crazy decisions. Wow, that's fascinating. So no planes had crashes involved with this or anything.
No, fortunately, nothing like that happened.
But if it had gone longer, that could have been a real threat.
Absolutely, and they would have shut down airspace. They flat out told us that at Seattle, that if it had been much longer, they would have shut down airspace. But also, by the way, even though we don't warn on that, we can't predict radio bursts, we do get those reports, thanks exclusively, by the way, to the U.S. Air Force, because they're the only one that operates this radio telescope network that monitors certain frequencies to encode those frequencies. That's how we knew this was going on, was from their reports. And we were able to immediately provide that when I heard from aviation that they were having problems. The problems I saw were frequencies that should not have been impacted just due to a solar flare. So it made me look, and I saw, holy cow, we've got this massive radio burst going on that we don't report on, but we could have to tell them now. And that helped avoid that problem too. Once they realized it was space weather, they knew it wasn't going to last too long, and they were able to avoid the problem. And they were able to use other means to communicate, but so nobody's lives was ever at risk, but it could have been if it lasted much longer.
So they have, you said there's alternative means. What exactly would that entail?
There's digital means of communicating on some of these frequencies that are a little less prone. In some cases, like the one in Seattle, even that was a problem. I'm not quite sure how they actually finally communicated, whether it was SATCOM or some other means over there in the Seattle area. But other places were able to use or eventually go to those other means, and they were able to communicate or just be heard enough to be understandable, because this really impacted the voice analog systems that were being utilized in most cases. So that's what I mean by other means. There's other things that aviation has out there. They always have to have a couple of backup methods of communicating. And fortunately, most of them were able to shift to that or do it. But, that's minutes of time. That's spinning up a new procedure or something. Oh, I need to go over here and get this tuned in and see if we can communicate. But meanwhile, if you had, let's say there was a nasty terrestrial weather day going on, the storms in the area and air traffic's already delayed and aircraft are orbiting around. Imagine what that could have been like if something like that had happened and been longer lasting. That's why, the safety issue came up. And if it lasted much longer, especially if there had been terrestrial weather, a problem as well, which there wasn't in this case. But if there had been, they may have been even quicker to shut down airspace.
Wow. Well, that's really interesting. And it's really interesting to know what's going on behind the scenes on these sort of events, because it seems as if there's not a crash or not some fatalities, it doesn't often make the news cycles, but there's still a lot of like pressing matters happening, whether there's regardless of the outcome. That's great that those are being monitored. Those are all ground-based satellites, those radio telescopes.
Those are ground-based radio telescopes.
Well, I think this has been such an interesting conversation. I feel like we could talk for hours here. Just as final thoughts, maybe what are some of the long-term ambitions and hopes SWPC would like to see implemented in the future, or some of the active projects that are being worked on at the current moments?
In the 9 years I've been here at SWPC, the first 4 or 5 years, I didn't see much new for changes going on. But all this new government legislation, executive orders, action groups have started developing. And now we're seeing a lot of things happen. We're seeing a lot of new scientists putting together models for operational use, whether it's flare probability forecasting assistance, better handles and ideas of where a coronal mass ejection might be going, radiation storms. That's always a really tough one to forecast. And we need to do that, especially when the astronauts are involved, because they're going to have to protect themselves out there. And that protection is not going to be easy. What they're going to have to do, they're going to be very cramped up already and then get even more cramped. We got to give them an all clear. When can they get away from that if one of these storms has enveloped themselves out there in space? So all of this exciting new stuff is starting to come in and become more available. More universities are getting involved with research, even having programs in space weather. So I guess what I'm getting at is things have been very slow to come up, and now we're really starting to see an increase, which is great because we desperately need it to do this job better. More spacecraft going out to replace old antiquated stuff that we're fortunate is still working. We need them out there, and now they're being funded and they're going to launch. So pretty exciting times ahead.
That's terrific. Any final thoughts or comments for the people at home on resources or things that they might want to look into more?
Yeah, I would say go to our webpage, swpc.noaa.gov, check it out, get familiar with it so you know where to go and be ready to go if you need to go there because of something that may be unfolding or something you hear about and you want to find the true facts on our webpage. And just be ready, be space weather ready. Learn more, all that you can to be ready in case we have one of these catastrophic like events progress upon us. And, know that we are behind the scenes forecasters at SWPC there, and we are making plenty of phone calls, contacts, sending out the watches, warnings, and alerts, letting the operators of our technologies get the information so they can take mitigation measures to decrease the likelihood of having some serious problem happen. So normally they should just be able to enjoy the aurora if we're having a geomagnetic storm and know that everybody's doing work to prevent a problem that we hope never happens.
Shawn, I really appreciate this. This has been a tremendous conversation, and I've learned so much. So I really appreciate your time, and thank you so much again for being here.
Yeah, Dr. John, it's been great. Pleasure. Thanks to you and your audience, and everybody be safe.